Hello, my name is Dr. Shannon Weiss. I'm an epileptologist and epilepsy researcher in Brooklyn, New York, and assistant professor of neurology, physiology, and pharmacology at the State University of New York Downstate. I'll be presenting to you our latest paper in brain communications entitled Graph Theoretical Measures of Fast Ripples Support the Epileptic Network Hypothesis. The predominant theory that has guided the practice of epilepsy surgery is known as the epileptogenic zone hypothesis. The epileptogenic zone is defined as a region that is indispensable for the generation of seizures. The epileptogenic zone is a theoretical construct and is inferred retrospectively as a region within the resection margins for patients who are seizure-free after surgery. A competing theory known as the epileptic network hypothesis was introduced by Dr. Susan Spencer. This theory posits that the changes that take place in the brain that allow the brain to produce a seizure may be widely distributed. Thus, an initial area of apparent seizure involvement may not really be an onset area because onset can be expressed in any part of the network. We sought to determine whether the epileptogenic zone hypothesis or the epileptic network hypothesis could better explain the outcomes of patients who underwent surgery in our study, but following the surgery exhibited no improvement of seizure frequency or severity. To compare the two theories, we used putative neurophysiological biomarkers of epileptic brain tissue known as high-frequency oscillations. High-frequency oscillations are brief bursts of spectral energy that can be classified as ripples or fast ripples. Fast ripples have been proposed to demarcate the epileptogenic zone because when they are incompletely resected, patients rarely have a seizure-free outcome following surgery. To examine networks of fast ripples, we use graph theoretical analysis, which can describe the global and local properties of networks consisting of nodes connected by edges. To investigate the epileptogenic zone hypothesis, we compared the accuracy of seizure onset zone electrode contact classification using high-frequency oscillation HFO rates in a cohort of 19 surgical responders and 9 surgical non-responders. We found that the accuracy of HFO and spike rates was not significantly different between the cohorts, suggesting that in non-responders, the epileptogenic zone partially encompassed the seizure onset zone and was presumably partially resected. However, when we compared the properties of the individual fast ripple events across the cohorts, we found that the responders had fast ripples with a spectral content greater than 350 Hz in the seizure onset zone, whereas the opposite was true for the non-responders, and also patients not offered surgery because of multifocal seizure onsets. Having established that fast ripples greater than 350 Hz were enriched in the seizure onset zone of surgical responders, but found outside the seizure onset zone in non-responders, we next asked if different network formulations of fast ripple generation could differentiate surgical responders from non-responders. The first network type examined rate distance and weighted the edge between two fast ripple generating electrode contacts by the Euclidean distance between the contacts multiplied by the average fast ripple rate of the two contacts. In this illustration, the color bar indicates the weight of the edge, and electrode contacts in a seizure onset zone are colored red. The global measure for this network was the radius of the network. Overall, we found that the radius of the rate distance network discriminated non-responders and patients not offered surgery due to multifocal onsets with 77% accuracy. The second network type examined temporal correlations between fast ripple greater than 350 Hz onset times across the fast ripple generating contacts, using mutual information to weight the edges. In the illustration, the size of the electrode contact is the nodal strength, and the color of the edge is the mutual information value. Overall, we found that in non-responders or patients not offered surgery, the path length of the mutual information network was often longer. The local efficiency, which is the inverse of the path length, in the non-seizure onset zone contacts was often lower. Also, the mean nodal strength ratio of the non-seizure onset zone contacts compared to the seizure onset zone contacts was often higher in the non-responders. To combine the graph theoretical measures from the fast ripple rate distance and mutual information networks, we used a support vector machine that was trained on the patients in the study cohort and tested on 13 distinct patients. We found that the support vector machine trained on the fast ripple network graph theoretical measures could distinguish non-responders in a test set with 92% accuracy at a blinded threshold. These results indicate patients who do not respond to surgery, or those not selected for resection or responsive neurostimulation, can be explained by the epileptic network hypothesis. And this is a decentralized network consisting of widely distributed, hyperexcitable, and relatively asynchronous fast ripple generating nodes.